I'm CG. I'm at Trinity College Dublin, and last year I did my master's research project at the University of Southampton, looking at a particularly funky calcium-rich supernova. So to bore you with this plot again, this is just the parameter space that we're looking at all these at. You've got the normal ones, then the funky, interesting ones, and the non-biased opinion of the best exotic ones, like the calcium-rich transients, faint and fast ones, so called because they're fainter than normal type 1As, and they evolve at the fast end of normal. And they're characterized most prominently by the very strong forbidden calcium-2 emission in the nebular phase spectra. So in that spectra, there are two distinct categories. You've got the photospheric phase at early times and the nebular phase at late times. And in the photospheric phase is when the ejecta is very hot, very dense, and very optically thick, and the photosphere obscures most of what's going on. So these spectra are very diverse between the calcium-rich sample, but they're all dominated by p-Cygni profiles, and most strongly in most of them is helium-1. And then as the ejecta expands and cools, and the photosphere recedes and shows more of the inner layers of the supernova, you get the nebular phase spectra. And this is how you characterize a calcium-rich supernova. So this is sort of like the fingerprint spectrum you'd expect to see. So you get these nebular emission lines that are forbidden emission lines that you can only get when the ejecta are in their low density environment. So for calcium rich, this is typically after 30 days, you'd expect to see these features. So you've got the big forbidden calcium 2, and then the smaller, if they're at all, forbidden oxygen 1. So this is what you expect to see. And this takes you on to my supernova, 23 XWI, which was discovered about a year ago now. And it was offset about 9 kiloparsecs from its host galaxy, which is normal for calcium rich. One of the key ways you find them is looking for faint and fast transients that are offset or remote from their host. So as I said before, the nebular forbidden transition lines you see late on after 30 days. However, for this supernova, you see forbidden calcium 2 from 1 day from peak, which is the second line, and it gets stronger as time goes on. And then you also see forbidden oxygen 1 really early on, clearly from 6 days from peak, and then it gets stronger and stronger, and then it goes away entirely at the end, which is weird. It shouldn't be that early. The ejecta should be too hot and too dense, and the photosphere should be extended too much. And you shouldn't see these, and yet we do. Plot thickens. So I did photometric investigation first, and I just looked at the peak brightness and the rise time, and both of these were in line with what you'd expect of a calcium-rich supernova. So it doesn't seem like anything's awry there. Next, I looked at the key ejecta properties itself. So the main ejecta mass from the explosion, the nickel 56 which powers it, and the calcium mass to see if excess calcium was the reason we were seeing this forbidden calcium line so early on. But all of these were in line with what you'd expect. So again, it doesn't seem like that's what's causing this weird stuff in XWI. And then finally, I looked at the photospheric velocity to see if it was an extra energetic explosion or something weird going on there that was causing this. But no, the photospheric velocity was again as you'd expect it to be for calcium rich. So what's going on? So I looked at the evolution of the velocity of these two features to see if that would give us more insight. And spoiler alert, it does. So from peak, it starts off at about 1600 kilometers a second. And then it settles down to about 0 kilometers at the truly nebular phase. So this is what we'd expect. At late times, you'd expect it to be 0 because it's when the photosphere is retracted, receded entirely. So you're looking at the core of the explosion, so you'd expect it to be 0. But this early velocity that isn't 0 causes problems / gives insight depending on your mindset. Because it's not 0, it's definitely faster. So you're looking at an area of low density calcium that's going at that velocity or that projected velocity. And this is much lower than the photospheric velocity. So it can't be that this was a clump of calcium that was chucked out from the explosion, because that would have immediately been overtaken and obscured by the supernova itself. So it has to be a low density region of calcium going at this velocity outside of the supernova. But calcium is synthesized in these explosions, so you can see where the problem lies. And then again, if I look at the oxygen 1 velocity, a similar thing happens. So it evolves from a much faster velocity at around peak to a much lower velocity at late times. Again, both slower than the photospheric velocity, so can't do that. And it doesn't settle at 0 as the calcium does, but we can't get a truly nebular phase spectrum for oxygen because it's so hard to distinguish from the continuum in the late time spectra. So this leads us to my model. This is based on AMC-VM systems, which you heard about earlier. So these are recurrent helium nova systems. So you've got two white dwarfs orbiting each other. One accretes helium from the other, and then periodically undergoes helium novae on its surface. And then this helium gets chucked out and caught in these polar lobes and forms these helium winds. And then also, these winds sweep up oxygen from the surface of the white dwarfs to form these low-density oxygen regions. And in more violent novae, calcium can be synthesized in this and gets swept up and forms these low-density calcium regions. So you have this sort of system going on. And then when the white dwarfs finally explode and you get your active supernova, you then see the P Cygni profile spectra at early times that you'd expect to see, but then you also get the forbidden transition lines from these external low-density regions around the supernova, which is what we see. So not only does this model explain the presence of these early forbidden calcium and oxygen-1 features that previously could not be explained, it also explains the velocity evolution, because initially you'd expect to see these nebula, forbidden emission line features have the velocity intrinsic to these external low-density regions. And then as the ejecta expand and mix in and the photosphere recedes, these would instead be dominated by the 0 velocity intrinsic to the supernova itself, which explains why it goes from a higher velocity to a lower velocity. So part 2 is what I'm doing now, my PhD, is investigating whether or not this model works for the rest of the calcium-rich lamp. And the important question is there early forbidden calcium-2 and oxygen-1 in the other stuff? And great news, guys, there is. So this is very preliminary investigation. Please do not commit this to memory yet. But I've looked at the whole historical sample we have of calcium-rich transients. I've looked at ZTF for anything that could possibly be a calcium-rich transient, and anything that has a non-zero velocity at early times, apart from this guy, settles to a much lower or a 0 velocity in its nebula phase. So this is in line with what the model thinks. For all of these, I've looked at the oxygen as well, and it follows a similar progression, but the oxygen is just much harder to fit because it's blended into the continuum in the earlier. But that's exciting. And then the other stuff that I have to do next is properly look at the velocity evolution of these features, see if the oxygen evolves in the same way as we saw in XWI with respect to calcium, and also see if I can find any transition features between the high velocity and low velocity states, because if you can see those, it would help us understand the physical processes at bay, as well as the scales of these kinds of systems, because we don't know how big I'd expect the system to be. So in conclusion, this model appears to unify all the calcium-rich supernovae, at least for now. It explains the early calcium-2 and oxygen-1 forbidden emission that we see, and the velocity evolution as well. Thanks.